Today's topic is on isosceles triangles and equilateral triangles. We're going to start by looking at the parts of an isosceles triangle. So this is isosceles. The two equal sides of an isosceles triangle are called the legs, and the angles opposite those legs are what we call the base angles. The third side of the triangle is called the base, and the vertex opposite the base, or here is the vertex which is located opposite the base. Now, first thing we're going to talk about is the isosceles triangle theorem, which says if two sides of a triangle are congruent, then the two angles opposite them are congruent. So let's just very quickly draw a triangle. So if you have two sides of a triangle that are congruent, those angles opposite them are also congruent. So these base angles are congruent, in other words. That is in an isosceles triangle only. Let's move on. The converse of the isosceles triangle theorem. If two angles of a triangle are congruent, then the two sides opposite them are congruent. So again, let's take a look. Here's a picture. If you know that the two base angles are congruent, then it automatically follows that the sides opposite them are congruent as well. The equilateral triangle corollary says a triangle is equilateral if and only if it's equiangular. So in other words, those two ideas are basically interchangeable. Let's see if we can draw this. Right, so if a triangle is equilateral, it also means that all the angles have to be congruent. I really don't need this other one that I just drew. Okay, now remember, all the angles in a triangle add up to 180 degrees. So if you have an equilateral triangle, you're going to have to divide those three angles equally among 180. So I will use this picture. So each angle would be 60 degrees in an equilateral or equiangular triangle. So let's move on. Let's say that you're given this diagram and you're asked to find x and y. Well, look at this. We see right off that this first triangle on the left is equilateral. So that also means it's equiangular. So it means every angle here in that equilateral triangle has to be 60 degrees. So we know right off x is 60. Now look at this. We have a straight line that's being formed at the top. So this 60-degree angle and the one right next to it, the adjacent angle to it, has to form a linear pair. So these two angles have to add up to 180. Therefore, this angle would have to be 120. Notice this triangle on the right. It's also an isosceles triangle. So we know that the two base angles are congruent. But remember, all the angles in a triangle have to add up to 180. So 120 degrees plus whatever these two equal angles are have to add up to 180. So let's figure out what those angles would be. If we take 180 minus 120, that gives us 60 degrees. That 60 degrees has to be divided among these two equal angles. So if we divide that by 2, we're going to end up with 30 degrees. So each of these angles ends up being 30 degrees. So y is 30. Now over here, the next diagram, you're asked to find x. You're given that the vertex angle is 50 degrees. This is an isosceles triangle, and you're asked to find x, which is one of the base angles. Well, since it's an isosceles triangle, the two base angles are going to be equal to one another, so this one's also x here. So think about it. These three angles have to add up to 180, so you've got 50 plus x, which has to give you 180. Let's combine our like terms, so we have 50 plus 2x. We have a nice equation here, which equals 180. Subtract 50 from each side to start solving it. So we have 2x equals 130. Dividing each side by 2, we get that x is 65 degrees. Now, you probably could have done this all in your head without an equation. That's fine. You don't have to do it this way. If you just weren't sure, I thought if by setting up an equation you could go back and check and verify why this whole thing works. Let's go on to the next page. Here we are given the angle A is congruent to angle B. Angle CED is congruent to angle CDE. So CED, which is right here, is congruent to angle CDE. And we want to prove that segment AC is congruent to segment BC. So we're going to be writing a two-column proof, so let's just make our lines here. And we're going to list our statements and our reasons. And so let's start by just listing what we're given. Angle A is congruent to angle B. That's given. And also that angle CED is congruent to angle CDE. That is given. Well, let's see what else we notice about these triangles. We've got two angles in each one that are congruent. If we can prove the two triangles are congruent, we can prove that their corresponding parts are congruent as well. So let's see. So what we can do, since we notice that triangle AED and triangle BED share a common side, we know that segment ED is congruent to itself. So we can say ED is congruent to ED. And that is the reflexive property. Now next, we have that these triangles now have angle, angle, side, so they are congruent to each other. So triangle ADE is congruent to triangle BED by angle, angle, side. Now, we want to show that AC is congruent to BC, but so we're going to have to do a little bit more manipulating here. If triangle ADE is congruent to triangle BED, then we know that segment AD is congruent to segment BE by CPCTC. We know that. Now, the other things that we know. We also know that we've got an isosceles triangle here right in the middle because we have base angles that are congruent. That's triangle CED. So if those base angles are congruent, we know that the legs of the isosceles triangle are congruent. So in other words, side CE has got to be congruent to side CD. Let's write that down. CE is congruent to side CD, and that is by the converse of the isosceles triangle theorem. Alright, so let's make this a little bit longer, which basically said that if you have two base angles that are congruent, the sides opposite them are congruent. So now let's see what else we know here. We know that AC plus CD will give you your entire segment AD, I'm sorry. AC plus CD equals AD, and BC plus BE gives you that entire segment BE. So let's write that down, and that's by the segment addition postulate. So we know that AC plus CD equals AD, and we know that BC plus CE equals BE. And that goes right back to the very beginning of the year with the segment addition postulate. Right? And remember, what we're going for is that AC equals BC. Well, we're almost there. We know that CE and CD are congruent. So we can substitute one for the other. We also know that AD and BE are congruent, so we can substitute one for the other. So this means that we can actually set these two pieces here, AC plus CD equal to BC plus CE. And that's just by substitution. If two things are congruent or equal, we can substitute them one for the other. Now, as I just said a minute ago, we also know that CD and CE are congruent, so we can substitute one for the other. So let's say we can write this really as AC plus CD is equal to BC plus CD. They have the same length. CE and CD have the same length. They can be substituted one for the other. So we're using substitution. Now we're almost ready to say that AC and BC are congruent. Think of this equation. If you went ahead and subtracted CD from each side, you would end up with the fact that AC and BC are equal. Or in other words, that AC is congruent to BC. And that is just by using your subtraction property. Now, you know, the other thing you can do here, you could probably reason through a lot of this on your own without even writing a two-column proof. If you wanted to write this out in sentences or in a paragraph form, that would be fine, as long as you're just stating the argument. So that's another thing to think about. And we'll be discussing this more in class, so bring your questions with you. Thank you for joining me.